There we go. Yeah, as you were saying that, I was clicking the button. I appreciate it because I forget. I totally appreciate it. All right, so we've been looking at limits. Everything we've been looking at so far has been limits to a specific point on the x. So is x going to something? Tonight we're going to look at x going to infinity. So we're going to look at limits at infinity, specifically horizontal asymptotes. So anybody remember what a horizontal asymptote is? Because you did learn this in pre-calculus. Yes. Yes, okay. What's a more specific definition of a horizontal asymptote? Yes.
It's like the limit as x approaches infinity and infinity.
Yeah, so it's a value that the graph, and a lot of times it will not cross it, but it can. It's where the graph, as x gets infinitely larger or infinitely negative, it's getting closer and closer to that point. And that's basically what this definition of the board says. So as the limit as x goes to infinity of f of x equals L, or the limit as x goes to negative infinity f of x equals L. They do not have to be the same for it to be true. So you can have problems that have two horizontal asymptotes, one going to negative infinity and one going to positive infinity. Okay, so they do not have to be the same. And we will look at least one case tonight where they actually are different. Okay, let's look at some graphs first, and then we'll look at some equations. All right, so here is a graph of 3x minus 1 over x plus 1. This is a rational function. And it's giving you the asymptotes dashed there. So what is the limit as x goes to negative infinity for g of x? It is 3. So the negative infinity one is this direction. That's negative infinity. And this one over here, that's the positive infinity. So in this case, they're both going to 3. And just because we've talked about it before, what's the vertical asymptote for this one? Yeah, x equals negative 1. It's where the does not work exist on the bottom. Is that a removable discontinuity or a non-removable discontinuity? Not a removable because it goes to infinity. Okay. I know it didn't ask you there, but other questions do. So. All right, so here is, so you can start to see the equations that become more crazy and possibly have different things are trig functions. So here's negative 4 arctangent of x over pi. So this is the graph. So as x goes to infinity, so one of those things that I will tell you on Alex really quickly is if you look down here, they are not always in the same direction, same order. Okay, so it's not always going to be negative infinity on the top and infinity on the bottom when you do your topics in Alex. Sometimes they will switch them on you. And if you don't pay attention, you'll put them in the wrong spot and you'll get it wrong and you'll be frustrated. So make sure you read and are answering the questions that they're asking. So x goes to infinity. What's the limit as x goes to infinity?
-2.
This is -2. So this is this side here, right? That's positive infinity, and this would be negative infinity. So negative infinity is going to what? Positive 2. That makes sense? Simple enough? Nothing crazy? The graph ones are typically pretty easy. So when we start doing the equations, it becomes a little more complicated. I see people frantically writing, so I'm going to let them finish writing. You're fine. Skip that one. I think I got a good idea. So actually, probably should have left that one. That's okay. I just realized what that one was. All right, what about this one? What is the limit as x goes to negative infinity? Is it going to a specific spot? No, as you're going further and further that way, what's it doing? It's going up and down faster, right? So this limit does not exist. Okay, that is a possibility that it does not exist. What about the limit as x goes to infinity?
One.
Yeah, that was going to the 1, right? Huh?
Realize the reason why I just want to say is like slowly tapering up.
Yes. Yep. Yeah, it's still going to bounce, but it's getting slower and slower. So as you go all the way out to infinity, it's in essence going to end up stopping. All right. What is the limit as x goes to infinity and not you? Why? Okay, but it has a dashed line. Doesn't that mean anything?
It's not.
That's a slant asymptote, if you remember from your pre-calc class. So yes, that doesn't actually mean anything in the situation, and it does go to negative infinity. What about the negative infinity as x goes to negative infinity? That would be going to positive. Yes. So my limits can go to negative infinity and positive infinity. That is a possible option for them. All right. Any questions on the graphs? Or are you guys good with the graphs? All right. All right, what's my horizontal asymptote? I'm going to totally test your pre-calc brain. What was the rules they talked about?
However, like the degree of denominators, figure the degree of the numerator.
Yeah, you probably did this. Numerator greater than the denominator. There is no horizontal asymptote. Numerator less than the denominator. It is y equals 0. If the numerator equals the denominator, it was the leading coefficient over the leading coefficient. And those are all degrees when you're talking about the numerator and the denominator. So in this case, my numerator here, the degree is 2, and my denominator, the degree is 3. So my horizontal asymptote is y equals 0. That was what you learned in pre-calculus. And it's still true. It's literally the right answer. There's nothing wrong with that answer. It only works with polynomials when you have polynomials on top and the bottom. When I have anything else, which we're going to be able to deal with, this is not going to work. We have to do other stuff. So we need to have some kind of a rule that's going to help us with this. We will get back and do this problem again in a second. But let's look at that problem. What's that limit going to? Why?
Because the degree of the numerator is 0. Because
Okay. Ignore the pre-calc. Stop thinking about the pre-calc brain. Just think about this problem. Think about this equation.
as x gets infinitely bigger, 1 over that bigger number is going to make that fraction smaller and smaller.
Yeah. So as the denominator is getting bigger and bigger, right? It's getting smaller and smaller. The fraction's getting smaller and smaller, right? Just in your rational brain, when you think about it, everybody gets that concept, correct? Okay. So would it matter if I change this to any exponent there? It would just get there faster, right? So like even if that was x to the n and n is any number, it's going to go to 0, right? Okay, perfect. That's actually going to be a very important rule. So here's the official theorem. So no matter what the r is, as long as r is greater than 0, the limit as x goes to infinity or as x goes to negative infinity, it goes to 0, which is what we just did. That's just the official written out explanation. All right, so now look at this rule again. All right, so what can I do to a fraction and keep it the exact same? So what can I do to a fraction and not actually change the fraction?
Multiply the numerator and denominator by the same.
Okay, so I can multiply the numerator and denominator by the same thing, correct? Can I also divide the numerator and denominator by the same thing? Okay. So if I took this problem here and I said 6 over x to the 3 minus 5x squared over x to the third over 2x to the third over x to the third minus 7 over x to the third, did I change the problem? No. I divided everything by the same thing, correct? Okay. So if we're looking at this now, I can simplify this a little bit. And the limit rules say I can do that limit to each piece. I'm never going to have you do this out, ever. Okay? So you can write it down so you see it, but I do not expect you to write this out like I'm writing it out right now. I'm doing this just so you can actually see what I'm going to be talking about. So with all those limit rules that we had, we can find the limit of each piece. Now, using the rule we just talked about, that new theorem, what's the limit as x goes to negative infinity of 6 over x to the third?
0.
That would be 0. 5 over x? 2. 7 over x to the third? So the answer is 0 over 2, which is 0. Okay? That is the calculus way to solve that problem. Comes up to the same answer. Okay, so what I call it is you have pre-calc brain, calc brain. Same answers, same things. It's just when we were talking about horizontal asymptotes, we were talking about typically end behavior when we were doing with in pre-calculus. You're looking at the end behavior uses. When we're looking at in calculus, we're typically talking about how limits work. And we're going to be doing a bunch of different types of problems with this, not just a polynomial over a polynomial. So this method allows you to solve those types of problems. We're looking at always dividing by the highest degree in the denominator. Okay, so whatever the highest degree in the denominator is, that's what we're going to divide everything by. Okay. What's what?
In the point, the limits, 5 divided by x.
Yeah.
You didn't write the x to the third, you said.
You're right, because I reduced it.
Oh,
X squared over x to the third goes down to just the x. Yeah. Same reason why those two are gone. That just happened to be the only one that was actually able to be reduced, except for the x to the third being gone. So, yeah. Because you actually don't want the x on the top. Because if you have the x on the top, it becomes now infinity over infinity, which doesn't work. So if you notice, actually, that's one very important thing about the rule. It is a 1 on the top. Okay. And even though I didn't necessarily have a 1 on the top, I had a 5. Remember, I can always take that 5 and move it out front, because I can pull out a constant. So it technically was still like a 1 over it. So the key piece is that is an integer or a whole, like a real number up there, no variables. So that canceling out is actually very important in that respect. All right. Let's look at this one. All right, so what am I going to divide each thing by?
X.
Dividing them all by x. So x, 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 x. So I get 1 over x minus 3x over 3 minus 5 over x. So this is how I would typically see you guys writing this. Now, if I did the limit of each piece, 1 over x becomes what?
0.
That's 0. Negative 3x or minus 3x, that's going to go to what? Infinity. And then I have 3 minus 0, so that goes to negative infinity. Yes.
So you're dividing by the highest degree of the denominator.
Of the denominator, yes. So your goal is not necessarily to get rid of all the x's. The goal is to get rid of the things that are going to cause you trouble with figuring it out and to prevent you from getting infinity over infinity. So if you were to divide everything by x squared, you'd have ended up getting 0 on the denominator, which we can't do. So that's where that problem comes in. That's why we always use the highest degree in the denominator.
How come the horizontal asymptote?
Oh, it does. This one does work. This one absolutely would work for this one. So my numerator is, my degree in the numerator is 2. My degree in the numerator or bottom is 1. So my numerator is greater than the denominator. So technically, I do not have a horizontal asymptote. So I don't have a horizontal asymptote because it goes to infinity. So they do work. It's just, it's not giving you. So in this type of situation, you'd have done it and like, okay, what's my end behavior doing? What's the right side doing? What's the left side doing? In this case, the right side, because it's a negative leading coefficient, it's going down. So it's going to negative infinity. So those rules still do work on some of the problems. They're just not always answering the question it's asking because of the way it's asking it. And in the next couple of problems, you're going to see where it doesn't actually work. Let's make sure nothing crazy in this one. Let me do one of those. Since I didn't do one with them both this year. All right. So what am I going to divide them all by?
X squared.
So x squared, x squared, x squared, x squared. So it's the limit as x goes to infinity of 5 minus 6 over x squared. 5 over x squared minus 2. So 5 minus 0, 0 minus 2. So negative 5 over 2. And now if we go back to the horizontal asymptote rules, the numerator and denominator both have the same degree. So we would look at the leading coefficients, which is 5 over negative 2. So
I remember the.
yeah, that's okay. The nice thing is you don't need to know. And it's we move past that type of thing, so you don't necessarily need to know them. If you can do it this way always works. Sometimes we kind of simplify things sometimes for the algebra and the pre-calc rules and stuff like that because you don't have an understanding of certain concepts. So like we really don't talk about limits when we're dealing with in pre-calculus or algebra until the very end of pre-calculus. So it's like we couldn't explain horizontal asymptote using limits because you hadn't learned limits. And it's hard to explain limits when you don't have a really good understanding of the graphs and those type of things to be able to understand limits. So it's kind of like, okay, how do we do horizontal asymptotes to get end behavior and those things without doing limits? They kind of came up with basically like a trick or an easier way to do it in certain situations. So, but this is where it all came from. It's just like when you get into Calc 2, you'll actually start learning how they do volume and whatnot. And that's actually where all the geometry equations came from. They just did it with calculus, but then they decided, okay, this is an equation that always works. It's what it reduces down to. So now we'll teach that in geometry without teaching you how they actually came up with that volume concept. So those little things. All right, let's do one that doesn't work that nicely. Like this one. All right. What is the degree in the denominator? So what am I going to divide? So thinking back to the same rules, we're not going to do any different rules. What am I dividing everything by? Dividing everything by x. So bottom by x, top by x. You'll notice I did not put it under each piece yet because of that square root. That makes my life a little more complicated. Bottom is simple. 3x over x minus 8 over x. That one works out nice. This one, I need to put inside the square root. So what would be the equivalent of the square root of what would give me x? Not you guys. You guys are answering a ton. Yes. Good. So I'm going to put in x squared under each of those. Everybody understand why? Because in essence, x equals the square root of x squared. So I'm in essence replacing that with that and putting it inside. So I have square root of 7 over x plus 6, 3 minus 8 over x. So now I can do the same rules that I was doing before, 0 plus 6 over 3 minus 0. So my limit is the square root of 6 over 3. Does that make sense how it works? And again, we're not really changing the rules or anything crazy with it. We're just figuring out how we can manipulate it a little bit to get it to the way that I want it. Let's look at this one. All right, try this one. All right, what am I dividing them all by? So I really want to get rid of this x squared, right? So I'm going to divide the bottom by the square root of x squared because that's really what I want to put inside, which is in essence what? X. So I'm going to divide the top by x. So I have 7 over x minus 5 Then I have the square root of 6 minus 5 over x squared. I skipped a couple steps in there while I was doing it out. Anybody confused? Do you want me to write about, or are you good? Okay, so the top's going to 0 minus 5. The bottom's going to square root of 6 minus 0. So I have negative 5 over the square root of 6. I am not positive if Alex requires you to rationalize, but if it does, then it'd be, remember, we multiply the top and the bottom by the square root, in essence, to get rid of the square root.
Can you explain that part?
This part,
Yeah, because I've had come across it where I put it in as the initial one, -5 over square root of x, and it said it was wrong.
so when you're rationalizing, the goal is to multiply it by itself to get rid of the root. So in this case, since it's squared, I only have to multiply it by one of them. So square root of 6 times square root of 6 is really the square root of 36, which is 6. And the top just stays.
And now it's rational.
And now it's rationalized.
And it was irrational before.
It's not irrational because it has a whole nother meaning. it's rationalized because you typically don't want to square root in the denominator of your function. Just aesthetics. There's no actual mathematical reason for it. It would totally work.
Just because Alex has used that as a way to not use that as an number.
It shouldn't mark it wrong, but I'm sure it does. Like I said, it shouldn't mark it wrong, but I'm betting it does at some point. On my test, I won't mark it wrong, just because it's mathematically they're identical. There is some situations where it makes life a little bit easier when you're trying to cancel things out and simplify things, especially when you're doing trig functions. Like you have like the square root 1 over the square root of 3, which is really the square root of 3 over 3 for certain like of the unit circle. Makes your life a little bit easier when you're trying to cancel things out. Doesn't always have to be that way. So, all right. Oh, actually, as crazy as it's gonna sound. I want to show you one thing first, because what was the one thing I always told you to do that we haven't been doing? What was the one thing you should always do when you're looking for limits? Just plug it in, right? Okay. If you plug this in infinity, you're going to get what? Infinity over infinity, basically, right? Which is undetermined. We can't determine that, right? Okay. There's a reason I'm saying that. Because of a problem like this. If, oh my God, we plugged in infinity to this, what would you get? Okay, and the square root of infinity is really infinity, right? So you get infinity minus infinity. And you might want to think, well, that's 0. But what happens if this infinity is getting there faster than this one does? Then it goes to negative infinity. Or if the other end happens, it could also go to infinity. We don't know. So it is one of the undetermined factors, okay? So just like 0 over 0 or infinity over infinity, infinity minus infinity is also one of those undetermined things, which means we need to be able to figure out a way to solve this problem to get it to be determinable. This one, as it sits, is not a rational function. Okay. So I can't divide it by anything, because if I divide it by something, I'm going to change the problem. A rational function's fractions. Anything is a fraction. So in this situation, what do you think we need to do? We've done something similar to this.
We change the square root to being to multiplying by the by 1/2, or like setting what
So, okay. So here's what I don't want you to do, because I have a feeling this is what you think you're going, or are thinking to doing. You're going to want to do this. So it's like, it'd be like 2x to the third plus 9 to the 1/2, or in this case, 3. Because that would be 4x to the 6 to the 1/2 plus 9 to the 1/2.
Yeah.
Okay? Those don't equal each other. It would be 4x to the 6 plus 9 to the 1/2, which really doesn't help us. Okay? Just like you can't distribute the square in, like, when you're doing foiling, you have to FOIL it out. You can't just split up the actual exponent like this and take the square root of each piece. It doesn't work out that way. So that's probably not going to help us. The reason I showed that is because I have people do that all the time. So like, I wanted to get out of the head of that little mistake that could happen. What is another way that we could possibly solve this?
use different or no. Take the square root.
What do you mean take the square root?
What I do is remove the constant and square root for x.
Okay. So in essence, you're looking at it very similar to what you did in pre-calculus. So you're looking at, okay, the highest degree is going to eventually take over that problem, right? The 9's not going to be worth much as you're getting closer to infinity. Just the 4x to the 6 is going to matter of it, and you end up getting 0. Because you get 2x squared, 2x to the third minus 2x to the third. Problem is that it goes back to what we just looked at a second ago, where you're breaking it down like that doesn't necessarily work. Now, I'm not saying 0 might not be the right answer. Honestly, I haven't done this problem. I don't know the actual right answer off the top of my head until I actually do it out. So 0 could be the right answer. That's possible, but it also could be the other two. So one of the methods that we talked about in one of the previous limit problems, when we're looking at going to the limit of a specific number, when we had square roots and things in it, we did its conjugate pair. Because the conjugate pair allows us to get rid of the square root by multiplying, basically by using the difference of squares rules. So if I multiply this by the square root of 4x plus 6 plus 9 plus 2x to the third, that would clean up the top. But did I change my problem? Yeah, because I can't multiply something and not change the problem. How can I not change the problem? What's the one thing I can multiply by that does not change my answer? Nope. Multiplying by -1 will definitely change the problem. But you're close. Multiplying by 1. As long as you multiply a problem by 1, it doesn't change, right? So I also have to multiply which I think was what you were talking about, was the reciprocal. I know. So I have to multiply by 1. That is 1. It's a messy 1, absolutely, but it is 1. So, and over here, I really have a 1 down the bottom because that outrights the denominator. So now, multiplying this out, I get 4x to the 6 plus 9 minus 4x to the 6th on the top, and square root of 4x to the 6 plus 9 plus 2x to the 3rd on the bottom. So now I get 9 on the top. And plus 2x to the 3rd on the bottom.
What did you make it, plus 2x to the third?
Nope.
Okay,
I want them to be difference because now I have the difference of squares.
okay.
Because if you remember the difference of squares was a squared plus b or minus b squared equals a minus b, a plus b. So in essence, by doing the difference of squares, I'm getting rid of that square root, which is causing me all the trouble. All right, so now I have 9 on the top. And if I plugged infinity into the bottom, what do I get? I get infinity plus infinity, right? Which doesn't matter what they go there, it's always infinity. So I get 9 over infinity, which would be 0, which is the answer. So 0 was the answer. Okay, let's do. Questions with that one? So when you have so in essence, when you get infinity minus infinity, you kind of have to do something similar to this to be able to make your life easier to figure out what's going on. Because as we learned when we were kids, infinities aren't all equal. Because infinity raised to infinity beats infinity. Infinity plus 1 is always better than infinity. I don't know if kids still do that today, actually. That was a big thing when I was growing up. It's like you start yelling at each other. It's like, I hate you, infinity. I hate you, infinity plus 1. It's like stupid little things we said when we were kids. And it was that the crazy part is, it was true. Infinities aren't all equal. All right. That's not what I want. Yeah, let's get rid of that one. I want that one. All right, do that one. So when you're looking at these questions, what it's asking is important. If it was x goes to infinity, you could just plug in infinity to do this problem. You have to do no actual work. Because I would get infinity plus infinity inside here, which is infinity, plus infinity, so that's just infinity, and we'd be done. Because of the negative sign in there, if you plugged it in, I would get infinity here, and I would get minus infinity here, which that's undefined. That's indeterminate. So I can't do that. So I have to do the breakout. And you can actually see this if you look at the graph. You can see on the infinity side, it goes to infinity really quickly. On the negative infinity side, it doesn't. So the question is where is it actually going to? So square root 16x squared plus 5x minus 4x. So I have the limit as x goes to negative infinity of 16x squared plus 5x minus 4x over. Oh, wait. 4x squared. Nope, not 4x squared. That's not 4x. I forgot to multiply it. 16x squared. So I get 5x on the top, square root of 16x squared plus 5x minus 4x on the bottom. So I'm going to divide everything by what? By x. So divide everything by x, which is in essence in here as x squared. So I have 5 on the top. I have square root of 16 plus 5 over x. Thank you. Minus 4. So when I plug in negative infinity, that goes to 0. So I have 5 over where did we screw up? Because it should be 5 over negative 4. Actually, it shouldn't be negative 5 over 4. That's right. That's right. Okay. We now know that I'm not flawless. I'm trying to find the problem again because I deleted it and now I have to go back and do it again. Did that. Got that answer. Why isn't it working?
It wouldn't be, uh, for the step where you got penalties, it would be, 5, that's for 16x, plus 5.
What was it?
And for step 4, the final answer would it be 5 divided by square root of 16x plus 5?
No. Here or here?
There.
Because the 5 x divided by x, and then the inside it's it's x squared. So that's how it gets to 16. Oh, there's there. Okay. Not intuitive error. This is why it didn't click. When you take the square root of something, what do you get? It can be positive or negative. We're going to negative infinity. So that square root's negative. So it's negative square root of 16 minus 4, which would be 5 over negative 8. That's the. If it was positive, we would be right. It'd be going to infinity, which is exactly what we said. If you look at the graph, it does. The negative infinity, you have to take the negative version of the square root. I'm sitting here looking, I'm like, I know this is not right. Why? There you go. Always a stupid little science. So that's where that negative comes back to haunt you. When you take the square root of 16, we get a negative 4. So you get the negative 8. Okay. One more topic in Alex that we have to go over. Let's do the most complicated one. All right, so this topic asks you to find a bunch of limits from it. And then I want you to identify any vertical asymptotes and horizontal asymptotes. All right, so find me my limits for each of those. That's the first one. What's the only change that has to happen for the negative version? When you do the square root, there's negative there. So it's a negative 3. Yes.
I'm confused on why the square root becomes negative when the limit is going to negative.
Because you're actually dividing by x squared, which doesn't have a sign. It eliminates the signs. So when you have to do when you take the square root, technically you always get a plus or minus version of it. So the plus version works for positive infinity, the negative version works for the negative infinity. So, and actually on this one, if we look at the graph, you can actually see it quite clearly. That's going to 3, and that's going to negative 3. So, and that's the other thing. I would highly suggest, like, when you're doing these to check them, just throw it on a graph and see what happens. You should get a good idea of what's going on with it. And that way I'll help you catch those little mistakes with like the signs and stuff. And for these, actually, when you're looking at them, these you really can't plug any numbers in to find them. So you kind of do have to look at a graph or a table for these. So this one right here, and as when we looked at the graph, that's over on this side here. So that's going that way. So it's going to infinity. And at the negative one, the negative square root of 3, it's also going to infinity, a lot quicker actually.
So there's no way to tell without the graph. or-
You can do a table. Remember, the very first thing we looked at was doing tables. So we would plug numbers in, getting closer and closer to that. So some of them you can, some of them you can't. Like in this situation, you're really, there's no other way to really do what's happening as you get this closer to the square root of 3 without doing it, because it's going close. And in essence, what you could do is kind of look and figure out what's going on, because what happens with this one, when you plug in the square root of 3, you get 7 plus 3x over 3 minus 3, which ends up going to, so it's going to 0. The question is since we're getting closer to that on the positive side, that number right there is really going to be bigger than 3 at every given point. So, but it's getting closer and closer to that. So since it's bigger, it's going to be a positive version. This is going to be a positive answer at the end of it. And it's getting closer and closer to 0. So as my denominator is going closer and closer to 0, what's happening to my function? It's going to infinity. So you can kind of like rationalize what's going on with it without actually doing out a table or looking at the graph. But at that point, looking at a graph is actually probably just as fast to do it than rationalizing it out. And the same thing with this one, when you plug in the negative square root of 3 for this, that actually gets rid of it because it's x squared, so it's still going to be 3. And every number before that is still going to be a bigger number because it's going to be a positive answer because you're squaring it. So the same rules would apply for that one as applies for that one. Yeah, it's still going to get closer and closer to 0.
But the top numerator would be 7 minus 3 squared.
But the numerator doesn't matter. The numerator
Well, it
makes,
would tell you what direction the overall infinity is. Right?
yes. Yes, it would. But since the 7 is bigger than that, the positive takes over. So even if that one was a negative, so this was minus, that's still going to be bigger. And that's actually why when we looked at the graph, this side gets there faster than this side does because of that, because of the numerator. So yes, in that case, when you're looking at it, in this situation, it didn't matter because the 7 was bigger, but it could matter depending on which one was there.
So for the test, will we be able to use a decimal spread?
Yes. Yep, you can. Anything I use in class, you can use on the test. So, all right, we're done.